Here we go. Okay. So again, in the voltaic cell, if you're given the picture and they don't label the anode cathode, they don't label the electrons, because if they label the electrons, wherever the electrons are coming from, that's your anode. Wherever they're going, that's your cathode. So that's another way to identify. It depends on the question. I don't know what they're necessarily going to show or not show, but this will never fail you. Go to table J. The more reactive is always the anode, which is oxidized. Let me explain why that makes sense. If you look at the left side of the chart, what do we learn about the group 1, group 2 metals compared to the rest of the metals? They're more reactive. Very reactive metals form cations, positive ions. So Na forms +1, Ca forms +2. Why do they do that? To get a complete octet, so they're stable. Well, if a metal loses electrons easily to form an octet, that means they like being oxidized. So the more reactive the metal is, the more it likes to lose electrons, the more it likes to be stable, full valence shell, which means it wants to be oxidized. So between these two, the more reactive one gets to do that. It's kind of like a privilege. It wants to lose electrons because that makes it more stable. Silver does not want to gain electrons. Metals do not like gaining. They like losing. Non-metals like to gain. But if you set up a voltaic cell, one of them is going to have to gain, one of them is going to have to lose, and it depends on reactivity. All right, so that will always work, and that's a very helpful piece of information for your homework, right? Because maybe you didn't know which one was the anode or cathode on the homework. Maybe you just assumed the left one is anode and the right one is cathode. Don't assume anymore. Now you can look it up. Okay, so I probably should have told you that the other day. That's really important to remember, okay, how to look that up. All right, and before we go over some of the homework, let's talk about a salt bridge, okay? Yesterday, I explained it to the students who were here, and then in period 5, I explained it a little bit different, so I'll do it the same way with you guys. So you guys who were here yesterday, just let the others figure this out. Okay, here we go. I thought this was clever. Maybe not. I don't know. Okay, this is Alaska. This is Asia. What's a salt bridge? What's the analogy? I think social studies.
The land bridge.
Land bridge! Haha! I always think this is so clever because it really helps kids remember, because social studies teachers teach this the same way. What's the point of the land bridge? Why did it exist? Or what are you supposed to learn about the land bridge? What happened? What did it allow? People and animals to migrate. That's the word. That's why I think this is clever, because you need to know that word migrate. So something is migrating between the two. These are called half cells. Between the two half cells, something is migrating between them. What's inside that salt bridge? NO3 minus K plus. Dylan, what are those called?
Salt.
Yep, very good. Give me another. So the salt would be KNO3. When it breaks apart, it dissociates into these things. What are those called? Ions. That's what a salt bridge does. It allows ions to migrate between half cells. So that's what we're going to write down. A salt bridge allows ions to migrate. And the importance of the salt bridge is if the ions can't migrate back and forth, the cell shuts down. Because you can't have too much charge on one side or the other, so the negative and positive ions have to be able to move to kind of balance out. So what do you really need to know? It allows ions to migrate. It allows ions to migrate. And I guess the very last thing with this, we need to write down, how do the ions migrate? The anions go to the anode and the cations go to the cathode. Anions migrate here, cations migrate over here, and cations, if you look up here, cations are positive. So look at the K plus, it's going this way. Ag plus is a cation, it's going to the metal. So all the positives are trying to go here. NO3 minus is a negative, it's trying to get over here. So all the anions are negative going to the anode. That's how it works in batteries too. So cations go to the cathode, which are positive, right? Cations are positive. That little T in the cation there, I always say, kind of looks like a plus, right? So cations are positive, and then anions go to the anode. Anions go to the anode. So if I had told you all of that on, I don't know, I'm losing track of my days here, Tuesday, you could have been able to actually probably complete the entire worksheet. Except number 12, I should have had you skip that. You do not need to know how to do 12. So if you didn't know how, that's good, because you shouldn't have. If you did know how, you know a lot more about chemistry than I thought. So 12 we're not going to go over. Alright, so now let's take what we learned and apply it to the homework. Let's go over that now. So answers 1 through 7 can be answered based on identifying which one is the anode, which one is the cathode. Okay? So I'm just gonna go over it out loud. I'm not gonna project this or write it on the board. So try and stay with me here. So you got Fe on the left, you got Cu on the right. Someone go to table J and tell me which one is the anode, which one is the cathode. So Fe and Cu, go to table J. Who's more reactive, Morgan? Fe, so that means it's the anode. So Fe is the anode. So number 1, the answer is Fe or anode. You could write the word anode or Fe. So the anode is oxidized, which specifically is Fe. Number 2, reduction occurs at Cu, which is the cathode. Again, anox, red cat. Those acronyms, Leo, Ger, really important to remember. Anox, red cat, fat cat. If you say them enough, you remember them, it really helps with lots of questions. 3 is Fe, 4 is Cu. Again, electrode means the piece of metal in the solution. 5, electrons will flow from which electrode? Mackenzie. Fe, right. Anode is oxidized. It loses electrons. The electrons go from anode to cathode. Good. Which will gain in mass? Kaylin. Cu, right. Fat cat. Cu will get bigger and bigger. I'm going to show you a video here after this, and it shows the anode losing and the cathode gaining mass. So 7 is Fe, or anode. Either answer works. It's losing mass. Number 8. To which electrode will the anions migrate? We literally just wrote that down. They go to the anode. So anions go to the anode. You didn't know that before. So anions go to the anode. You could also put Fe for that, either one. Number 9 and 10 you should have been able to do. The anions are NO3 minus. The cations, there's 3 options. Fe plus 2, Na plus, and Cu plus 2. Those are your 3 ions, cations in the cell. 11, to which electrode will the cations migrate? You write cathode or Cu, either one. Cathode or Cu. 12, we're skipping. 13, 14, I'll come back to that. 15, we just learned, migration of ions, or allows ions to migrate. That's what a salt bridge does. You'll see when I make the voltaic cell next week, I make my salt bridge instead of using this super cool YouTube. Because what you do with this is you actually make a really, it's almost like a paste. It's like a thick solution, like viscous we'll call it. That's not a good way to explain it, never mind. But it's a thick solution, and you fill this up with your salt solution. You take cotton plugs, actually, just like cotton balls, and you stuff them in here. Then you turn it upside down, and you put 1 beaker here, 1 beaker here, and that allows the salt solution in here not to drain out into the beakers. It's interesting how that works. It works pretty well. So the ions can go back and forth through this. But instead of doing all that, which is complicated, I just make a saturated salt solution and crumple up a paper towel, put it in the beaker, take out the paper towel, fold it neatly, and I use that as my salt bridge. It works well. And I can show you on the voltmeter, you'll see electricity, and then I'll pull the salt bridge out, and it shuts off. I put the salt bridge back in, it turns on. So it's very obvious when you see it, the importance of the salt bridge. It's for the ions, but without those ions moving, it's kind of like a complete circuit here. You have your electrons going through the wire, and your salt or your ions going through the bridge. So it's like a circuit. So if you remove one of those pieces, it doesn't work. So anyways, it's cool when you see it. Makes more sense. All right, so that was 15. Okay, 16 and 17. If you go up to the picture and look underneath it, I gave you the reaction. You have Cu plus 2 plus Fe solid yields Cu solid plus Fe plus 2. So here's your reaction, and it's already balanced. So you have plus 2, and you have 1, 1, 1, 1, 1 of everything, so it's already balanced. These two are 0, right? The solid metals are 0. So if we want to do the oxidation half reaction or the reduction, either one, first thing we have to figure out, Mariana, is which one of these, Cu plus 2 or Fe0, which one's oxidized, which one's reduced? Hold on. I have confidence you're going to get it right, but I'm going to give you a hint and everyone else a hint. If you're given a picture of the voltaic cell, and you know the Fe is the anode because you went to table J and it's more reactive. So if you know that's the anode, and then you remember an ox red cat, you know Fe, this side, this beaker, is oxidation. And you know Cu is reduced. So if you know all of that, it makes this easier. This has to be reduced. This must be oxidized. Why? Because Fe, we just determined, is the anode, and that's oxidized. Copper side is reduction. So one side is oxidation, one's reduction. So the copper is reduced and the iron is oxidized. So I didn't let you answer that. But that's how what you learned today about the cell can help with that. Were you going to say that anyway? Okay. All right, so oxidation, Fe0. Cu plus 2 is reduced. All right, so Fe0 turns into Fe plus 2 because it lost electrons. Shane, how many electrons did Fe lose? 2. Very good. Plus 2E minus. Very good. And if iron is losing 2, Laura Grippin, how many electrons is copper plus 2 gaining? 2. And it turns into Cu0. So there's your answers to 16, 17. The left half cell is oxidation. That's the top one. And the right half cell is reduction. And there's one more thing I want to mention here before I go over the agents quick, and then I'll show you that video. Fe is solid metal. When it loses electrons, the metal turns into an ion. That's why this metal will slowly deteriorate. But if you look here, the ions are combining with electrons and forming copper. So your copper electrode is going to get bigger and bigger because this is making more copper. Where your iron is breaking down, your copper is being formed. So that explains why your anode loses mass and cathode gains mass. But the video shows it a little bit better. All right, and now real quick, 13, 14. Oxidizing agent would be Cu plus 2. Reducing agent, Fe0. If you wrote just Cu and just Fe, it's wrong. You need to specify with the charge which Fe and which Cu. Because this Cu over here, look up here please, this Cu is not being reduced or oxidized. That's the result of the reduction. So that's nothing's happening to that, it's being formed. This Fe, nothing's happening to it, it's being formed. So these two are being oxidized and reduced, so therefore Cu plus 2 is your oxidizing agent, Fe0 is a reducing agent. You gotta label those charges or else it's gonna be marked wrong on a regents. You can't just write Fe and Cu, you gotta specify. All right, that's important. Okay, so that's that. Let me show you the video, and then I'll put the picture of the electrolytic cell up for you to copy down. Lights, please. All right. Don't need that anymore. That was good. All right, here we go. So it's kind of blurry, but it's a good video when they zoom in. So let me explain a little bit. You have zinc here, and you have copper here. This is the same cell I'm going to show you next week, except mine doesn't have all fancy apparatus here. Anyways, here's your salt bridge. That's the YouTube, and there's plugs in there, but you can't see it. So this is a zinc bar. This is copper bar. In here is copper nitrate solution, and in here is zinc nitrate solution. Both solutions are electrolytes. What does that mean? Electrolytes. Marcy, what's an electrolyte? Yes, very good. This solution conducts electricity, and so does that one. If you have a battery, you're holding a battery, everything inside the battery helps electricity be produced or conduct. That should make sense to you. So in a voltaic cell, any solution that's used is called an electrolyte. It just depends on which one. This one must have copper ions. This one must have zinc ions in there because this is zinc and this is copper. So it always kind of matches. Anyways, the electrons are flowing from the zinc up here into the copper. They don't have a voltaic cell. So this is your anode, this is your cathode. Again, table J. Zinc is more reactive than copper. That's how we would figure that out. All right. So they're going to zoom in and show you a little bit. I just think it helps seeing it. Here we go.
Atomic scale and see how this cell operates. Here at the anode, the site of oxidation, zinc atoms in the metal bar are in contact with the surrounding electrolyte solution.
Yep.
Each atom loses 2 electrons and becomes a zinc ion.
Okay, so there's your oxidation. Zinc loses 2 electrons, forms Zn+2. You saw what happened. The zinc that was on the bar literally breaks off in the solution. So now it's an ion. That's why the anode will get skinnier and skinnier and start to deteriorate, because all these atoms are losing electrons and falling into solution. So that's why the anode gets skinnier.
Diffuses into the solution.
Or loses mass.
The electrons given up enter the bar and join the flow of electrons up toward the external circuit. They travel through the wire and flow into the cathode, the site of reduction. When a copper 2 ion in the cathode solution makes contact with the copper electrode, it gains 2 electrons and is reduced to a copper atom.
Okay, so you saw that copper +2 floating, floating, floating. Once it touches the bar, this has electricity running through it, electrons, same thing. It gains 2 electrons that were sent over from zinc, so the copper +2 in the water gain 2 electrons, then jump on the bar. So now you're forming more and more copper. That's why the cathode, fat cat, gets bigger and bigger. So the cathode gains mass because of this reaction. So we can write all the problems on the board all we want, and I can go over and over, but I think seeing it is better, right? I think it helps you understand a little bit better. There's a little more to the video, but I'm going to stop for the sake of time. So that's the gist of a voltaic cell, okay? So all that stuff we just talked about, hopefully it's making sense. Okay, so next one, copy this down in your notes. This is an electrolytic cell. Let me just try and see if I can make that a little bigger here. All right, so this is an electrolytic cell. That didn't really help. Hopefully you can read that. So in this one beaker, so you have one big beaker, you have 2 pieces of metal, one's the anode, one's the cathode, connected by a wire to a battery. Inside the beaker is an electrolyte solution, something that conducts electricity. And in this one, it's salt. It's NaCl. I wish I could zoom in a little bit, but that'll screw up my whole thing here. Yeah, I don't know. Hopefully you guys can see it. If I zoom in, that messes with all my pages and whatnot. So, you have salt water, or actually it might be molten salt. I can't determine from the picture which one it is. So it might be liquid salt, which also conducts electricity, or it could be salt water. In this case, I think it's actually liquid salt. So this green stuff here is liquid salt. You have Na+, Cl- ions. When you melt ionic solids and they're in a liquid form, their ions are free to move around. So kind of works the same way, conducts electricity. So this is an electrolytic cell. The biggest difference between the 2 cells, this one only has 1 beaker, so there's no salt bridge. The other huge difference between voltaic and electrolytic is that the electrolytic cell here is non-spontaneous. So there's a battery. You have to hook this up to a battery. It needs power. It needs electricity. That's the biggest difference between voltaic and electrolytic. So again, this is called the electrolytic cell. We wrote the name down the other day. It needs a power source. And the 2 common reactions we talk about are electroplating, putting metal on other metals. I'll show you that next week. And electrolysis, where you can like separate compounds, separate water with electricity. So that's what electrolytic cells do. Bless you. They use electricity to perform chemical reactions. That's what they do. Whereas a voltaic cell is the opposite. It uses chemicals to produce electricity. And if you can see this here, underneath Cl-, you have 2 Cl- yields Cl2 plus 2 electrons. And over here, under the cathode, you have 2 Na plus 2 electrons yields 2 Na liquid. So everything you learn about the voltaic cell applies to this. Anox, red cat, fat cat, the electrons flow from the anode to the cathode, so nothing new to remember. It's all the same. The only difference, again, is this needs a power source, whereas a voltaic cell is a power source. So again, if you look at the left side here, Cl minus is losing 2 electrons and becoming chlorine gas. Over here, Na plus is gaining electrons and forming Na liquid. So I'm going to write those on the board a little bit bigger so you can see easier. So we have 2 Cl minus turning into Cl2 plus 2 electrons. So this is what's happening at the anode. It's losing 2 electrons and becoming a gas with a 0 charge. And then on the reduction side, you have 2 Na plus gaining those 2 electrons. This is reduction, and forming 2 Na liquid. So these two, the Na plus is gaining and the Cl minus is losing. That's what this is showing here and here, if you're having trouble seeing that. So again, anode is oxidized and cathode is reduced. So what's actually happening is you're forming sodium metal on this bar right here. So Na liquid is actually being created over here. And that's because this is ridiculous. This is probably 800 something degrees. It has to be if it's liquid salt. So anyways, you're going to get liquid sodium out of that because it's reduction. So that would be the electroplating part. You can actually create metal, plate metal using this, and I'll show you that. So as far as like the gist of the electrolytic cell, I just went over everything. All right, there's nothing really new for me to write down for notes. Anox, red cat, anode loses electrons, cathode gains. The only tricky part is, can you write the half reaction? So if I gave you this picture without giving you the half reactions, could you write them? That worksheet, I think, is asking you to do that. Yeah, so the number 76, that worksheet due Monday, the very last question is asking you to write a half reaction. We'll see if you can figure it out. We'll go over it, obviously, but it's writing those half reactions. All you need to remember, anox, red cat, and that should help you with that. What else was I going to say about this electrolytic cell? A lot of times on the regents, they will maybe like open up the circuit, and then they'll say, you know, what's one way to, you know, explain why this doesn't work, or what's one way to get this cell to work? And the answer is close the circuit. So, you know, if there's a break in the wire, that's why it doesn't work. I mean, I feel like that's obvious, but I feel like I should mention it. That's a common question. Questions on this? I feel like I'm throwing a lot at you, but a lot of it is the same information. No questions. Okay, so again, this bar here will gain mass. This bar will lose mass as this thing runs. Even though it's not a voltaic, it's the same principle. Okay? Oh, and there's one more thing here. Cl minus, Na plus. Which one is the anion? Kira, which one's the anion? Cl minus, Na plus. Cl minus. So, anions go to the anode. So all the Cl minuses are going to accumulate over here, and the Na plus, they're all going to migrate towards the cathode. So cations go to the cathode. It makes a little more sense in this picture, and here's why. The anode is positively charged in an electrolytic cell, so the negative will be attracted to the positive. Same thing here. Cathodes are negative, so the positive ions will be attracted to it. So that's a little bit easier than in the voltaic cell. But again, the anions go to the anode, and the cations go to the cathode. So no questions on this. Still got a little bit of time. Okay, so I think what I'm going to do with the few minutes that we have left, I'm going to take this off. I'm going to draw another cell. I'm going to tell you what's in it, and then I'm going to have you practice writing a half reaction. See if you can do it. We'll go over it, and that'll be it. Okay? And I'm leaving early, so I will not be after school. If you need anything, just to let you know. Lights, please. All right, so I'm going to draw another one. You draw this as well. All right, so let's say in here we have AgNO3AQ. So let's say we have silver nitrate solution. So then we have a battery up here, and we have a positive, negative terminal. We have a piece of metal here. All right, and we have a piece of metal here. Okay, one's your anode, one's your cathode. This one, I think, I'll tell you, this one's actually your cathode. This one's your anode. Okay, copy this down. So you got your battery, you got your electrolytic cell here. So my question to you would be, could you write the half reaction that is occurring at the cathode? So we want to write the half reaction at the cathode. And all I gave you was this picture. So you have silver nitrate solution. You have two metals inside the solution connected with wires to the battery. Could you write the half reaction that is occurring over here? I would be willing to bet most of you would say no at this point because we haven't practiced at all. So let me help you out and then I'll give you a minute to try and do it. Ag plus NO3 minus are floating around in here. So Ag plus and NO3 minus are floating around. The Ag plus is attracted to one of those, anode or cathode, and the NO3 minus is attracted to the other one. So based on which ion goes to the cathode, you should be able to have a better idea of how to write the half reaction. I just erased it over here, but it was just like this one here. So the Na plus gained 2 electrons and became Na0. What would happen in here at the cathode over here? So what would the half reaction look? So we're doing reduction, right? Anox red cat. So you're going to be having, something that looks like this. I'll give you a minute. See if you can figure it out.